today's lab, we'll be synthesizing the artificial scent of hyacinth. This lab began last week, where we took transenamic acid and we brominated it in order to form the dibromo compound, and this week we'll undergo an elimination reaction in order to form the alkene, and we'll be looking at whether or not this alkene is of the cis or trans stereochemistry. In the first step of the reaction, we're going to use an appropriately sized weigh boat. We're going to be weighing out about half a gram of material. So you can see that I chose one of the smaller weigh boats, and I've tared it on the balance. Now I'm going to weigh out my potassium carbonate, and you can see that we're using 0.549 grams of potassium carbonate. I've transferred this potassium carbonate to a 50 ml Erlenmeyer flask, and I'm adding 8 mils, about 7.9 mils exactly, of DI water to this flask. First, add the water to the flask. It does not dissolve. However, upon swirling the flask, it now has formed a clear solution. Now I've obtained one of the microwave reactors. These are thick, heavy-walled vessels, and they have threading in order to allow for pressure buildup. I am resting this microwave tube, since it has a round bottom and a beaker, to make sure it doesn't fall over. And I want to transfer about a third to a half of my potassium carbonate solution into this vessel. And now I'm going to weigh out the dibromocinamic acid that we synthesized last week. So we had exactly 0.550 grams. And you can see that I've added this, and I'm now going to add the rest of the potassium carbonate solution. Now, here we see the compound, which does not dissolve in the water, and we can see the lid assembly. There's an inner lid, and then there is a screw top lid on top of it. And it's really important that we make sure that there's no compound blocking the sealing of this joint. This is going to be under high pressure. In order to completely seal this, we're going to use a little tool to make sure the lid is well ratcheted and of the proper tightness. Now we see that there is a small glass tube. This only happens on one sample, and it's going to allow us to measure the temperature within one of these reaction vessels to control the temperature of the program. And you can see that there's a large amount of undissolved solid. Here is the rack in which all the tubes go on for the microwave reactor, and we've put our sample in which the probe goes into in position number 1. Now we're securing a lid. This lid is secured on, so should something go wrong and there be a glass explosion, it only affects a single sample vial, and it does not affect we do not have glass flying around the microwave. We contain the glass into one slot. Here is the microwave. It's not our normal household chemical microwave. The white tube on the left-hand side, is used to vent the gases into the hood. We have now started the program. You can see, if you look carefully, you can see our tray. You can see that if you look carefully right here, you can see the tube, the probe that is measuring the temperature within our vessel. The microwave has been running for almost 3 minutes now, and it is currently at 121 degrees. Now this is 121 degrees centigrade. Recall that water boils at 100 degrees centigrade, and we're going to go up to 125 degrees centigrade. The only way that we can get up to these temperatures is to have extremely high pressure. This is similar to the process in pressure canning, in which a high pressure allows you to increase the temperature over the boiling point of water at 1 atmosphere. So in order to get water to be boiling at 21 to 125 degrees, we have extremely high pressure within this vessel. Now, we have finished our microwave run. It was 11 minutes to run after that 3-minute warm-up period, and we've allowed them to cool down until they can handle. And I've taken this out, and there's something I'm not too happy about. The part that I'm happy about is all my transenamic acid has reacted, and we don't see any undissolved solvent. But if we compare this to our reaction at the beginning, we see that there is substantially less volume. That means that some of my solvent or perhaps some of my product has evaporated out of the tube. And so we need to take this into account when we're thinking about the reasons for lost yield, is that there was a substantial amount of evaporation out of the tube. Now I'm going to transfer my product into my separatory funnel, and I have now weighed out 5.5 mils of methylene chloride or dichloromethane. I'm using that 5.5 mils to rinse any of my product into my separatory funnel, which you see here. You can see the two layers, the dichloromethane and the aqueous layer on top of it. And I'm now going to repeat that process with about 4.8 mils of dichloromethane, and we can now see that our organic layer on the bottom has become larger. I'm now going to add 3 molar KOH. You can see there's about 5.2 mils of 3 molar KOH. When we add this, you can now see that the aqueous layer has also become larger. I'm going to shake the separatory funnel well, which I could not do while I was photographing it, so you don't see that. Allow the layers to settle. I've now drained the dichloromethane layer off, and I am adding another 5 mils of dichloromethane, and once again shaking this up to make sure that I've extracted all of my product into the lower organic layer. Now we want to wash our layer, and instead of draining the aqueous layer out the bottom, we need to pour it out the top. So we've drained the dichloromethane. We are now pouring the aqueous layer out the top. We're now returning the organic layer to the separatory funnel and measuring out 6.1 mils of water. This is just DI water that we're going to once again wash the organic layer with. We can now see the two layers. We're going to drain our lower organic layer. And now we're going to dry this with sodium sulfate. On the video, you can see swirling to make sure that the sodium sulfate has completely dried the solution. And now I've teared a cork ring. I want to make sure that I have something to support my round bottom flask. And I've now obtained the weight of my round bottom flask. It's 36.402 grams. So make sure to note that in your notebook. Now I'm going to remove the drying agent. Now some people like to remove the drying agent by making fluted filter paper. I prefer to fold the filter paper into a quarter and now open it up in the ring. That's just less work for me than fluting it. And here you see my setup. I'm supporting and resting the round bottom flask on the cork ring, and I'm supporting the filter by this funnel, and this allows me to pour my solution in it. Remember, my goal is to get all my product dissolved in my dichloromethane off. I don't need to transfer all the sodium sulfate to the filter paper. So I used several mils of dichloromethane to transfer it. Now, once I had all of my dichloromethane solution into my round bottom flask, I blew air over the solution in order to evaporate the dichloromethane into the hood, but I could have also set up the Rotavap and used the Rotavap to remove the solvent. The advantage of using the Rotavap is it allows us to reclaim the solvent, so that's usually a better choice for removing organic solvent, is to apply a vacuum and remove it into the Rotavap. Now you can see I only got a little bit of this colorless oil that smells as if what you smell in soaps and things that are designed to smell like hyacinth. You can see that I've now weighed it, and now my round bottom flask plus this oil is 36.482 grams. And so if I subtract the mass of the round bottom flask, I can obtain the mass of my product. And we're also going to post the GC information, but I filled a GC vial with a little bit of this sample, and we'll be looking at the GC.